Network Pathways problem 7.5. This particular problem gives us an XY, 3XY plots. What is supposed to represent a wave, okay, which is a sinusoidal oscillation. So on these particular plots, the y-axis is a measure of the amplitude of the wave, and this x-axis would be spatial or distance. Measure in meters, centimeters, nanometers, units, okay? But some measure of distance. Now it gives us three waves, and part A through, I think it's officially C or D in the problem, asks us to rank these waves by frequency, amplitude, wavelength, and energy, just based on the pictures, okay? And to be able to do that, you basically just need to understand what these terms mean. Okay, so let's start with amplitude. I think that's probably the easiest to see. Amplitude is nothing more than basically the distance from the peak of the wave to the trough, okay? Top to bottom of the sinusoidal waveform. So just by glancing at these pictures, I could see that wave number 1, or A, has the largest amplitude. It oscillates from -1 to +1. And the other oscillations, well, they're definitely sinusoidal in nature, or approximately sinusoidal, because I can't draw very good, right? The other waveforms have amplitudes that are smaller than this one, okay? So if I'm ranking by amplitude, I would say first would be wave A, because it's the largest from peak to trough. And after that, it looks to me in my drawing here on the board that C comes next. I wish I was a little bit more careful with my drawing, so I'll accentuate that a little bit, because the peak to trough here I think is a little bit bigger than it is here. Okay, it looks like maybe this comes up a little bit higher and down a little bit lower. So I might rank C next in amplitude. And then lastly, B. But there are other terms that we also want to understand. The next one will be, we'll say, frequency. Let's do wavelength first. Wavelength first. Okay, now wavelength, nothing more than the distance required for one complete oscillation. So when I say one complete oscillation, you can track that from the top to the next top, from the bottom to the next bottom if you want, from the midpoint all the way through one oscillation to the next midpoint, but you got to make one complete wave cycle through a maximum and minimum. That distance is the wavelength. Okay, so the distance required for one complete oscillation. It doesn't matter if you go from baseline to base through one complete oscillation to baseline. You can go from bottom to bottom. You can go from top to top. As long as you make one complete oscillation, you're golden. Okay, so that's what we're measuring for our wavelength here. So which has the highest wavelength? Well, it seems to me that if the x-axis is all the same for each plot, which it should be to make any meaningful comparison here, that's the wavelength there. Wavelength here, this would be a complete oscillation, right? So if I'm ranking those distances in order, I think it's C, B, A, right? Based on what I'm seeing in my picture here, C, B, A. C's got the longest wavelength, A's got the shortest. Now frequency is a measure of how many oscillations occur per second, okay? How many oscillations occur per second? It's measured in per second, cycles per second, or else in hertz units, which is the same as cycles per second. It's the number of oscillations that occur every second, okay? It can also be measured as the number of oscillations that occur per unit distance, provided all the waves travel at the same velocity. So these electromagnetic waves do, so that's also a valid thing. And you can write the number of cycles per centimeter, say, or per distance. Okay, and sometimes you see that actually. It's called wave number in chemistry. It's used a lot when you talk about infrared rays for infrared spectroscopy. Okay, so we're looking at the frequency with which the waves oscillate, basically, per unit distance or per unit time, depending on the way you want to look at it. So it makes sense then that that's kind of like the opposite of the wavelength, right? If this distance is the same in all of my plots, frequency is essentially how many waves or how many cycles can I fit in to that space. So in that particular case, it looks to me like the highest frequency wave is A, because I get the most oscillations in my space, and then B comes next, and then last, the lowest frequencies are over on the right, C. Notice that frequency and wavelength then are kind of like opposites, right? The order for CBA for wavelength, but it's exactly reverse for the frequency. And that makes a lot of sense based on our discussion of what wavelength and frequency is here, okay? And then we have one more, the energy, right? Energy of the wave. Now, this one's hard to see graphically, I suppose, but there is a formula that we learn about in this chapter to compute the energy of different photons of electromagnetic radiation. Now, this is the energy for a single photon of electromagnetic radiation, a single particle, like most fundamental particle of light, okay? But what you can see, and what I want you to remember, is that energy is proportional directly to frequency. This is the frequency, okay? So energy and frequency scale together. So whatever answer we got for a frequency has to be the same for energy, because the two are directly proportional. So A, having the highest frequency, would be the most energetic, followed by B and then C. There are some follow-up questions that your book asks here. It tells us that wave B, which is this one in the middle, barely fails to cause a current when that light is shining on a metal. Which wave might cause a current when it shines on a metal? All right, now, I know what they're getting at with this problem, but if you're like unfamiliar with this stuff and these concepts and what this chapter is about, you haven't read it, like this problem is going to be a complete nightmare for you. You're not going to have any idea what in the world the book is talking about. What do you mean wave B barely fails to cause a current? Like, what are you talking about, okay? Well, what this question is asking you about fundamentally and trying to get you to understand is something called the photoelectric effect. Photoelectric effect. It's an important topic in this chapter, okay? Albert Einstein, actually won Nobel Prize for studying and describing this particular effect. And basically what this is if you take a metal, I'll put this just a big chunk of metal here, okay, and you shine light onto that metal, sometimes what happens, and we'll describe what we mean by sometimes here in a second, okay? Sometimes what can happen is we get this type of reaction to occur. Now this is just a generic reaction where the metal combines or interacts with the light. I have H nu here. H nu, same H nu as here, because that's energy from a photon. Light can carry energy, so this is really a packet of energy that our metal absorbs. And under some circumstances, what can happen is the atom of the metal can become a positive ion and release an electron. Okay? So the metal atom on the surface can become ionized to M+, and electron can be released from the metal surface. Alright? And this is called the photoelectric effect. But there are some details that we haven't considered yet. It turns out that this H nu, or the E energy packet, the magnitude of it, or the amount of energy, is very, very important here. If the energy packet is too small, this reaction doesn't proceed. But if the energy packet is large enough to overcome an ionization energy for this metal, then the reaction happens and we get electrons. Okay, so what problem B is getting out here is it's saying that this wave just barely fails to cause a current. So the energy of this wave is just barely insufficient to make this reaction go. Because if the reaction goes, we get electrons, and we can collect those electrons at an electrode, and that causes a current, okay? So that's what they mean by cause a current. It's basically causing a current in a wire. We can measure that, and that tells us that this reaction is happening. This photoelectric effect is happening. So in part B, they're telling us that this wave is barely insufficient energy to make this happen, okay? When the light shines on a metal. So which of the other waves might cause the photoelectric effect to occur? Okay, so now we kind of understand a little bit more. We should pick the one that has higher energy packets. Now C has a lower frequency, a longer wavelength, and a lower energy, right? So because of that, this is not likely to work at all compared to B. We know that B didn't work, so C is not going to work. But what we should do is we should pick the most energetic, or any more energetic waves. And our only choice here is wave A, because this is the highest frequency, the highest energy wave, and this one might work to produce a current via this photoelectric effect, okay? So this is an example of a problem where you read it at first, and you have absolutely no clue what's going on, right? What do you mean, causing a current on an electrode? I don't know. But if you put the question in context with some other topics in the chapter, like this photoelectric effect business, it makes a lot more sense, right? And that's a good example why just working through these problems is always a really good idea, right? Because you learn something, generally speaking, when you just sort of sit down and work a problem. All right, so the last part then, it tells us that wave B in the middle is supposed to represent visible light. If that happens, which one of these waves might be infrared or IR? Well, we already said that infrared light is a little less energetic than visible. It's got longer wavelengths. Okay? So the logical choice to me is that C could be infrared because it's got a longer wavelength, it's less energetic than our visible. And as a consequence of that, you might project that this wave might be ultraviolet, or even maybe even X-rays if the wavelength is short enough, because it's the most energetic. It's more energetic than visible. So if this is visible, that might be UV, maybe it's X-rays, okay? You don't really know because it's not a quantitative scale or anything of the sort. But again, we're just making these kind of general, generic conclusions based on what we see, all right?